Good morning, everyone. Yeah, this is Dr. S. Venkateswarlu, working as a professor of VC at IARE Hyderabad. Yeah, today we are discussing about DSP, overview of DSP, digital signal processing. So here under DSP, basically we're having the five models. First model is followed by review of discrete time signals and systems. So here from this module 1, we are having this all contents, discrete time signal with definition, signal classification, elementary signals, after that transformation of elementary signals. Okay, so concept of digital frequency, after that discrete time system definition, using the different systems. So it is useful in the digital signal processing when compared to prerequisite and so on. System classification. Under this linear time invariant system. After that properties of the linear time invariant system. Okay, time domain analysis of discrete time systems. So impulse response, the convolution sum. So methods of evaluating the convolution sum. So filtering using the overlap save and overlap methods. So after that, realization of digital filters. Using this, we know that all digital filter impulse in infinite impulse response, finite impulse response filter like IARE and FIR filter. So after that, realization of structures for IAR and FIR filters using what you call direct form 1, direct form 2, cascade, lattice, and parallel. This is the overview of whole and soul of the model 1, that is followed by review of the discrete time signals and system. Okay, so here we know that all this is the overview of DSP, digital signal processing, in terms of how it is varies that all signal or whatever it is. So here we are input already. We know that input. If you want to implement that all DSP, digital signal processing, we require that input. The input may be a .wav file or analog signal or sensor or whatever it is. The time. So if once you are given to this all, it is varies what things are required here. So for this case, so this course provides the design of discrete time system, which was like a DSP, digital signal processing course, provides the design of discrete time systems and analytical tools to analyze discrete signals and system. So using this all what do you call DSP, it focuses on the classification of the discrete time signals, okay, and systems. So within this linear time invariant system, how it is varies. After that, we are going to involve the discrete Fourier transform. In between that linear time invariant system, discrete Fourier transform, we require then suppose you have to recollect this Fourier series and Fourier transform. After that, how it is importance with this is you can analyze that linear time invariant system and discrete Fourier transform. So after that, fast Fourier transform algorithms for this under digital signal processing. So digital filter design and multi-rate signal processing. After digital signal processing applications are used in speech processing, maybe image processing, okay, audio and video data compression. So major one is the communication system. With this is a major application related to this what do you call electronics and communication engineering. Not only this particular stream, it is so many applications are involved. DSP, digital signal processing applications are used in different streams or different domains. Okay, so here all are we know that all analog signal. These are all fundas of this all digital DSP and so on. So here in this case, somewhat here, what do you call that signal? Signal classifications. Signal may be classified into periodic and aperiodic signal. So next, classification energy and power signals, deterministic and probabilistic signals, causal and non-causal, even and odd signals. Yeah, the signal process, signal properties. Periodic signal, signal is periodic if it is what do you call fixed, or if it is repeats itself after the fixed period, the period in terms of the t, yeah, the t, it is how it is varies that where x of t, where in terms of that x of t, where x of t is equal to x of what do you call that, x of t plus capital T for all t. The sign of t signal is periodic. The smallest value of t naught that satisfy the periodicity condition of this equation is the fundamental period of what do you call that, x of t. Within this t versus the x of t, graphically we write to observe this, whereas the t versus x of t. So we are right to verify that where t naught is the smallest value of the t naught that satisfy the periodic condition of this what do you call, where x of t, where x of t is equal to what do you call x of t plus capital T naught. Okay, for all t, yeah, for all t. So like this, the smallest value of the t naught that satisfy the periodicity condition of this equation is the fundamental period of x of t. So within this, so signal classification is involved. So our world is full of signals, both natural and man-made. Okay, so examples are the variation in the air pressure when we speak, the daily highs, what do you call, and lows in the temperature, and the periodic electrical signals generated by the heart. So signal represent information. Often signals may not cover, or signals may not convey the required information directly, and may not be free from disturbances. Okay, so it is in this context that signal processing forms the basics of enhancing, extracting, storing, or transmitting the useful information. Electrical signals perhaps offer the widest scope for such manipulations. Okay, so within this signal represent the information. Often the signal may not convey the required information directly and may not be free from disturbances. Like this, so our world is full of signals, both the natural and man-made. Okay, so within this, in fact, it is commonplace to convert signals to electrical form for processing. Okay, so this is the common. It is the common place to convert the signals to electrical form for processing. Okay, so here we have seen this here where analog signal, how they are representing the x-axis the t versus x of t. So how it is sampled signal. So now it is n versus x of n. So of that quantized signal, we have to verify that graphically, where x-axis the t versus xq of t. Okay, and so on. We will expect the digital signal n versus x cube of n. So normally, if we are identifying, we are using that signal is x of n, where x of n is a continuous time signal. So using this continuous time signal, after that, we are right to observe that x of n, that parenthesis change, where x of n is discrete time signals. Like this, the signal, analog signal to up to what you call how it is varies the discrete or continuous or whatever it is. So we try to verify this. The value of the signal at any instant corresponds to its instantaneous or to its amplitude. Okay, time may assume a continuum of the values, either maybe t or discrete values n or ts. The ts already we know that the sample or sampling interval and n is an integer. Okay, so like this, the amplitude may also assume a continuum of the values or be quantized to a finite number of discrete levels between its extremes. Yeah, this results in four possible kinds of the signal. Is one is analog signal, sample signal, quantized signal, and what you call distant signal. Graphically, we try to verify this all from analog signals to distant signal. Now it is varies from an analog signal where t versus x of t. Here it is assigned x of t, t, t versus x of t, or in sample signal where n what you call that n versus x of n. So the quantized signal where t versus what you call xq of t, and so on. We will expect that all distant, that distant signal xq of n. The parenthesis change here. It is observed that all where a continuous time signal and discrete time signal, where it is xq of n is the discrete time signal versus n. Right, to verify that in terms of this is what we call distant signal. Okay. Yeah, like this, the signal processing, how it is happened, how it is varies in terms of the signal from analog signals to what you call up to what you call whether it is CTS to DTS, continuous time signals to discrete time signal, how it is varies, we will see. Yeah, in the music we hear from your computer disc or CD player due to change in the air pressure caused by the vibration of the speaker, diaphragm is an analog signal because the pressure variation is a continuous function of the time. Okay, however, the information stored on the compact disc is in digital form. It must be processed and converted to analog form before you can hear the music. Yeah, this is the process. How it is from this music to the CD player to change its the pressure caused by the vibration of the speaker from is analog signal because the pressure variation, the continuous function of the time. Okay, a record of the what do you call yearly increase in the world population describes the time measured in increment of year and so on. The population increase is measured in the increment of 1% or maybe 1. Okay, so it is a digital signal which discrete values for both time and population. Here is the real time. That's why always we are in the real world. Wherever you go, we are observing the signal because of it is interpreted. The population increases is measured in the increment of 1. That 1 may be a person. Yeah, it is this is signal with discrete values for both time and population. Okay. Like here, by using this here, we are ready to distinguish that analog signal processing and digital signal processing, how it is varies, what the importance, what the merit and demerits, is it can verify. So there's after that we are ready to justify our DSP, digital signal processing, after the signal with the signal processing, how it is varies. So from this, analog signal have been the subject of much study in the past. From the beginning, what you call signals and system, before that signals and system, probability theory, stochastic process, or maybe what you call TSP and so on. Yeah, in recent decades, distress signals have received increasingly widespread attention because of throughout globe. They will expect that all digital era. That's why in recent decades, the digital signals have received increasingly widespread attention. So, being the members, they can be processed by the same logic circuits used in digital computers. So that's why it is a popularized in artificial intelligence, machine learning, data science, the cyber security, and so on. So in recent decades, digital signals have received increasingly widespread attention. Being numbers, they can process by the same logic circuits used in the digital era or digital computers. Two conceptual schemes for the processing of the signals are illustrated. Here it is as per this graphically. It is mentioned that analog signal processing. Second one is digital signal processing of analog signal. So in terms of this, both analog signal processing, digital signal processing, the input is same. The analog signal is input. So with this, they say the digital processing of the analog signal requires that we use an analog to digital converter. Okay, so here the ADC, analog to digital converter, for sampling the analog signal prior to the processing, and digital to analog converter to convert the processed digital signal back to the analog form. Yeah, that's right. Here it is mentioned that in terms of analog analog signal, this block diagram, and digital signal processing of the analog signal with the analog. That's why it is formed that a very what do you call the design aspects analog and digital signal processing. So here the analog signal, here it is analog signal processing. That input is analog signal. Okay, where maybe CTS, continuous time signal, maybe analog signal. Maybe here it is, you can consider this analog signal, maybe what do you call continuous time signal. It is given to that analog signal processor. We will expect this analog signal output. Similar case, in digital signal processing of the analog signal, where input is analog signal, we have to consider here also analog signal may be either speed signal, maybe dot wave file, or maybe dot WAV file, and analog signal or continuous time signal, okay, or analog signal. Consider this, it is given to that analog digital converter. Okay, click on this analog digital converter. What things are available here? This is a pre-filter. Pre-filter. So where that pre-filter, it is considered that all it is nothing but what we call low pass filter. Low pass filter. We know the significance of this low pass filter. It allows only low frequency signals. It opposes high frequency components. So that's why here the analog to digital converter. So we will expect this analog to digital converter output response is digital signal. Either maybe digital, say here that input signal is continuous time signal. Here we write to expect this either maybe continuous time signal, or this we write to verify that it is maybe a discrete time signal, or maybe we have to observe that either digital signal, either it is digital signal or we are representing, but discrete time signal or we are representing. Suppose we have to in depth of this digital signal processing subject course, try to verify this R to either maybe how it is distinguished this continuous time signal, what you call discrete signal as well as discrete time signal. Okay, that output is given to that digital signal processor. Okay, so using this all processor, we will expect that all here also digital signal, the accuracy digital signal. Why this case is not accuracy? Because of here. So what here? So this output response digital signal, that output signal is given to this, what do you call, this is a converter. Okay, this is analog converter. A distance to analog converter to convert the process signal, digital signal back to the analog signal. That's why we're ready to expect this output response is analog to analog signal only. That's why we are using this all, what do you call, the digital processing of analog signal requires that we use an analog to digital converter for sampling the analog signal prior to the processing, and a digital to analog converter to convert processed signal back to the analog form. Okay, so few other technologies have revolutionized what you call revolutizations the world as what you call profoundly as those based on the digital signal processing. A best example is, it is mentioned that best example in terms of this, the technology of recorded music was, what you call, until recently completely analog form, end to end, and the most important commercial source of recorded music used to be the, what you call, LP. That's the long playing record. It's long playing record. So the advent of the digital compact disc has changed all that in the span of just a few short years, and what you call and made the long playing record practically absolutely, it is verified. Signal processing, both analog and digital, forms the core of this application, and many others will be observed with reference to this. Technologies have what you call revolutionized this word as what you call probably is that as those based on the digital signal processing. So within this, so we have to implement this all our things. We require the sampling, the sampling of the analog signal, where this is analog signal. Okay, where it is in terms of this. Okay, that analog signal is often a matter of the practical necessity. It is also the first step in the digital signal processing. Here we know that all DSP with reference to this, where input the analog signal, it is given to that all analog to digital converter. Click on this. There is a pre filter. That pre filter, the filter is the free filter is followed by what you call the pass filter. Okay, so after that is given to that what you call, okay, that DSP processor. DSP processor, output of DSP processor. We have to verify. After that, it is given to that what we call distance to analog converter. We will expect this particular output response is same one. Okay. So now the process has analog signal by digital means. We must convert it to a digital signal in two steps. First, we must sample. We must sample it. Okay, you must sample it typically at a uniform interval Ts. Discrete quantity n Ts is related to the what do you call that? These are all the discrete quantities. Either maybe what you call in terms of n, or maybe Ts, or maybe what do you call x. Graphical representation for these all cases here, that the T versus x of n and so on. The T versus what do you call n versus like this, where x of n or whatever it is. Okay, that means we are using this discrete quantities n, where discrete quantity n and discrete quantity Ts, like this, and what do you call, is related to the integer index n. Integer index n. Next, we must quantize the sample value, like what do you call, amplitudes, like x-axis and amplitude values. Here definitely from this origin, so that amplitude values are maybe increase or decrease or whatever it is. You must quantize the sample value or sample values, maybe it is what we call amplitudes. Both sampling and quantization leads to potential loss of information. Okay, so what that loss? So here the potential of the loss of either it is sampling and quantization leads to a what do you call leads to a potential loss of information. So loss of information is we are unable to exploit the accuracy information or accuracy signal. The good news is that the signal can be sampled without loss of information if it is band limited to a highest frequency. Okay, and sampled at intervals less than what you call 12 fps. So this is the celebrated sampling theorem. Okay, so the bad news is that there is a good news that the merit and demerit is the bad news is that most signals are not band limited, and even small sampling interval may not be small enough. So this is the importance of what you call sampling and quantization. Sampled at interval less than that. This is the celebrating the sampling theorem. Using this particular theorem, we are going to implement our desirability like electronics systems and other digital era process. Okay, like this. Now coming to this discrete time signal definition and signal classifications. Within this, so the term signal is generally applied to something that convey the information. Okay, so signals may, for example, convey the information about the state or behavior of a physical system. Okay, so physically we try to verify this all either the signal is generally applied to the something that convey the information. Signal may for convey the information about the state or behavior of the physical system. As another class of examples, signals are synthesized. So how it is synthesized, you will see that the next level onwards. But once consider this, the signals are synthesized for the purpose of communication. Okay, information between humans or between humans and mission. I am talking about the DSP. So the mission, how they are agreeing that how they are receiving my goods. If you are considered nearby that mission or whatever it is, signals are synthesized. That time the signals are synthesized for the purpose of communicating information between the humans or between the humans and missions. Okay. So although signals can be represented in many ways, in all cases, information is contained in some pattern of the variations. It's like signals are represented mathematically as a function of one or more independent variables. Okay, so a signal is pattern of variation of the sum, what you call sum form signals are variables that carry the that carry the information. Okay, so here in terms of this here with that where it is CTS continuous time signal. Okay, so the continuous time signal or function of the real augment x of t, where here that x of t is the continuous time signal. Understood? So we are talking about that all where in terms of the x of t, or maybe we have to use that all x of n. Okay, this is all nothing but continuous time signal. Okay, so this continuous time signal. After this, you have to verify, distinguish between continuous time signal and discrete time signal. Okay, so in continuous time signal are a function of a real augment x of t. Okay, where the t is assigned. A t can take any real value of x of t, maybe a 0, okay, maybe a 0, okay, for given range of the values of t. The t is assigned either initially 0, 1, 2, 3, and so on. Okay, so coming to this DTS, discrete time signal. Discrete time signal are functions of argument that what do you call that takes values from the discrete set. It is here the discrete set is depending upon what you call x of n. Here x of t and x of n, where n from n, where if it is this value, okay, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, and so on. Integer index n instead of time t, okay, for discrete time systems. X may be an array of values. If you are using the multi-channel signal, values for X may be real or complex, like this we are to assign. Okay, next coming to the in-depth of the discrete time signal. The discrete time signal or discrete time signal is a time series consisting of the sequence of quantities. Unlike a CTS, continuous time signal, a discrete time signal is of both in terms of the here continuous time signal. We know that it is followed by x of n or maybe x of t. Coming to the DTS, discrete time signal, where discrete time signal is followed by what we call x of n. Okay. So, continuous time signal, a discrete time signal is not a function of the continuous argument. Okay, however, so it may have been obtained by sampling form or sampling from continuous time signal. Okay, sampling from continuous time signal. Okay, so when a discrete time signal is where if it is discrete time signal is obtained by sampling the sequence at uniformly spaced times, it has an associated sampling rate. So of that discrete time signal, the DTS discrete time signal may have several origins, but can usually be classified into one or two groups. It is assigned by acquiring the values of analog signal at constant or maybe what you call variable rate. This process is called sampling. You know that just now we have verified the sampling, importance of the sampling. Yeah, by observing the inherently discrete time processes such as like a weekly peaks values of the particular economic indicator. Yeah, real time it will ready to verify. Okay, so like this. So this is the overview of this all. Why we are learning the DSP, digital signal processing. Okay, yeah, the DSP is involved. So the DSP, there is a suppose you have to learn that all DSP found to in depth of this or DSP, digital signal processing. Okay, digital signal processing. So there is initially the introduction to the DSP, the fundamental aspect of DSP. So once we arrive this all awareness that the stuff is required, once we arriving this all DSP, fundamental aspect DSP of that, we are to verify that a digital, what you call digital speech processing. Okay, after that multi-dimensional digital signal processing. These are all related to one-dimensional cases. That is one-dimensional cases. Coming to the two-dimensional, that image, digital image processing. Here it is, two-dimensional case. With the multi-rate DSP, with the VLSI DSP, how they are fabricating, how they are using the what you call SOCs, system on chip. The time they require the multi-rate DSP or VLSI DSP. It is recognized. This is where distance speech processing. It is recognition purpose they are using. If the two-dimensional for understanding, yeah. If it is SOC purpose and so on, it is the DSP processes. But VLSI and other sophisticated application they require the DSP. Without this all DSP, there is no real-time what do you call electronic course. Okay. After that, advanced topic in what DSP, beyond that all DSP, advanced topic, it is specific or application specific system. Application specific system. This is involved this that what do you call the DSP, digital signal processing. After that, it is there is interlink this DSP with the information theory and coding technology. So it is involved the data compression, error control coding. It is also using this all efficient communication system. But here there is accuracy information and accuracy recognition, accuracy understanding purpose. So in the mobile communication or mobile, there we are using the mobiles. So we require the all processors. The time either which processor they are using. Okay, normal processor. Normally there is ARM processor. Now it is all are changed. That all present trend or processor they are using. Now for the data compression, error control coding. Here is the efficient communication system. Efficient, that is without any error or noise, without any noise, without any what do you call information is deviated. We'll expect this all are what do you call efficient communication system. The time we require the DSP as well as information theory and coding technology. Okay, so of that here it's all digital modulation, information security, multimedia security. It's somewhat reliable system security communication system is involved. So wherever we require this all DSP. Okay. Now, somewhat using this all the basic background of the DSP or whatever it is. The signal is already we have seen. Basic discrete time signal we have verified. Somewhat classification of discrete time signal is ready to enter. Basic operations on a discrete time signal of that. What is the importance of this DSP and so on. Okay. So here, basic discrete time signal. Signal is a function of one or more independent variables. So now it is here we are right to verify this all are so it is really how it is happened. Okay, so it is where is this all? Signal is a function of one or more independent variables which contains some information that can be conveyed, displayed or manipulated. How it is signals are manipulating? The time we require the signal function of one or more independent variables, so which contains some informations that can be conveyed, displayed or manipulated. Say for example, voice signal. I am talking about the discrete time signal, basic discrete time signal. How it is various real time and signal is a function of one or more independent variable. These are nothing but voice signal. So voice signal how it is varies, and video signal, biomedical signal. Like biomedical signal, already we know that nowadays present COVID scenario. So all biomedical signals are wherever we go, everybody having that all awareness of ECG or EEG and so on. What the importance of this all are affected with this all. Okay, biomedical signal on telephone wires and so on. These are all real time things. The time we require somewhat try to verify using these all signals, how it is involved with the discrete time signal and so on. Okay, so this is the involvement of these types of signals. Basically already we have seen that the signals are splitted. One is continuous time signal, or maybe consider continuous time. Next, discrete time or maybe discrete time signal. Discrete time signal. So in continuous time signal, we have to verify that the continuous values. Based on these continuous values, so we are ready to verify the term of the signal. This is the outcome. When input signals are available, the signals may be either CTS or continuous values are observed or not, finally there is a deciding factor is another. Similarly, the DTS, discrete time signal or discrete time, so either it is involved with the continuous values or discrete values. Okay, both are continuous and discrete. If it is continuous value, we have to verify that discrete. If it is discrete values, we have to verify that what you call digital signal. Using this all CTS and DTS, there is CTS, continuous time signal. So what we know that so what it is, continuous signals are defined as continuous in time, continuous in the amplitude. Best example is speech signal and audio signal and so on. Similarly, the discrete time signal. Using this all discrete time signal, so the discrete time signals are discretized in time and what you call continuous in amplitude. So they may also be defined as sampled version of the continuous time signal. Like here it is rail track, the rail track signal, and using this all continuous time signal and discrete time signal, we will expect that all what you call after maybe a digital signal. When a digital signal digitized in the time and quantized in amplitude, they may also be defined as quantized version of the discrete time signal. Okay, like this is the classification of the signal. The signal is defined as any what you call as any physical quantity that varies with the time, space, or any other independent what you call variables. Mathematically, we describe the signal as a function of one or more variables. Like here, it is assigned that where that signal, like a signal is carries information in the form of the signal carries information in the form of speech. Like I'm talking about signals. Next, music, or maybe image. Image may be a two-dimensional light intensity function. Maybe what you call video, and so on. The signal can be a function of the one or two or an independent variable, where capital is independent variable. So using this all directly we are right to split this all classifications of the signal. Here using this all are here the continuous time signal classification of the signal is classified. One is continuous time signal and discrete time signal, where this is the continuous time signal, where x-axis is the t, where y-axis is the amplitude, okay, amplitude positive values, amplitude negative values. Okay, discrete time signal, where x-axis is small n, y-axis is the what do you call amplitude, positive amplitude or negative amplitude values. After that, real-time aspect using the solar is you can verify that x-axis to x-axis to y-axis, how we are representing the continuous time signal or discrete time signal. Here, the classification of the signal is continuous time signal. Here it is mentioned CTS. This is continuous time signal. Here, so where t versus n, a, here x of n, where it is continuously positive going transition, negative going transition. Again, it is positive going transition, or maybe positive peak and negative peak. Then positive peak and negative peak. Now, cycle, first cycle, one cycle here, and one more cycle. It is continuous time signal. Yeah, coming to this discrete time signal, same, but here it is x-axis is the n. So where y-axis is the same, positive amplitude, what you call, here it is negative amplitude values. Here it is samples are here, like this. You need to verify the discrete time signal positive. Here it is positive going transitions and negative going transition. Again, this is positive going transition and negative going transitions. Here it is all. So this number of samples are A, that is here, negative amplitude. So easily you can compare the continuous time signal and what do you call discrete time signal. Okay, like this, if it is continuous time signal, we are right to verify even signal. And even signal is any signal either f of t, such as generalized equation is f of t is equal to f of minus t. Even signals are symmetric about vertical axis. Yeah, there is option in real time verification for this all either is frequency versus amplitude, or the time versus amplitude. If we are using this equation f of t, where f of t is equal to a into cos of omega t. If f of minus t is equal to a into cos of minus omega t is equal to a into cos of omega t. So these values are according to this frequency and amplitude values are observed. So we can verify in real time. Even signals are symmetric or not. Even signals are symmetric about vertical axis or maybe different axis. Right? To verify the real time here it is mentioned as per the even signal. How it is the even signal? Even signal is any signal. It is considered, it is followed by f of t such that generalized equation is f of t is equal to f of minus t. So click on this f of t, where f of t is a into cos omega t. F of minus t is a cos minus omega t is equal to a into cos of omega t. Using this all mathematical expression, graphically we write to verify here. So I have chosen that the frequency is 3 kilohertz, 3 hertz, and amplitude is 2. I have chosen. So now I am verifying that what you call generalized equation f of t is equal to minus f of minus t. With reference to this, you can verify that what you call based on this frequency 3 hertz and 2 amplitude. Okay, so like this here amplitudes are positive 2 and negative 2. According to the amplitude value, the time based on the time, that frequency using the solve frequency where the time period. So we know that all capital T, the T is equal to capital T is equal to what you call time period. So you need to calculate that reciprocal of the 1 by T is ready to verify that all frequency. But here it is the frequency is assigned. Frequency is assigned 3 hertz, isn't it? With reference to the graphical it is observed. Graphical representation while using generalized equation f of t, that what do you call f of t is equal to minus f of minus t. Here minus f of, right, here it is minus f of minus t, like this, right, to verify. But here by using this continuous time signal maybe even or odd. If it is odd signal, an odd signal is any signal f of t such that generalized equation f of t is equal to minus f of minus t. Okay. Now here it is, I have chosen that what do you call frequency is increasing. Here previously I have chosen the three hertz. What happens? Just now we have verified. So I am increasing that frequency. Previously the 3, now it is frequency is increasing. That amplitude also previously I have chosen only 2. Now I have chosen that what do you call 3. So based on this, practically the signal variation, continuous time signal is either odd signal or even signal. See here it is assigned that minus 3 amplitude plus 3 amplitude value with reference to that frequency. The frequency, the time period is, we know that the frequency is assigned 5 hertz. Right. Yeah, generalized, we know that all generalized equation f of t is equal to minus f of minus t, but as well that how it is that frequency is increases, the amplitude also increases, how it is graphically variation in a continuous time signal. Okay. Next, odd signal, go on increasing the odd frequency, how it is varies. Previously, the frequency is what you call 5 hertz, here it is 7, like this. Go on verifying this all. Okay, that amplitude here is 4, minus 4, plus 4. So the amplitude is 4, the frequency is 7. Here I have chosen the frequency is 7 already, where the amplitude is 4. So it is varies that odd signal. The continuous time signal with the odd signal, it is varies according to f of t. F of t is equal to minus f of t. Okay. So like this real-time aspect, we will try to verify this all signals, continuous time signal, either the odd signal or even signal. Now coming to the under continuous time signal, periodic signal, periodic and aperiodic. The continuous time signal, how we are verifying the periodic signal? A continuous time signal is a periodic if it repeats the itself after a constant period of the time. So this is the theoretical aspect of this periodic signal. A continuous signal, a continuous time signal is periodic if it repeats itself after a constant period of the time. So now it is followed by, we have to represent the mathematical equations of this, where x of t plus capital T, small t plus capital T is equal to CTS, that x of t. We have to use that all interval minus infinity less than t less than infinity, where capital T is, we know that one, period of the signal. Okay. So we are representing graphically with the help of the t versus same value, that is amplitude increases or decreases either the, so due to this all are we are to verifying the t value, the time the t is the period of signal. How we are verifying the graph real time? So go on using the periodic signal. If it is the t values using this all are, the t is here, it is only that periodic signal, only positive peak is appeared. There is no negative peak here, isn't it? Only positive peak, positive off cycle, only positive off cycle. What about negative off cycle? Because the negative off cycle is not appeared. So now it is considered that what you call a continuous time signal is periodic if it is repeats itself after a constant period of the time. Minus infinity less than t less than infinity, where t is the period of the signal. This is the period of the signal. So normally we know that all signal is like this. Okay, here positive going transition and negative going transition. Here the one cycle, positive off cycle and negative off cycle. It is nothing but one cycle. The time period is what we call capital T. But this case is the periodic signal. How it is represent this what we call the continuous time signal and this periodic signal and the continuous time signal. Like this, right? Observe both the mathematically and graphically. Yeah, next one is continuous signal, a periodic signal. An opposite of the periodic signal is a periodic. It never repeats. Although technical a periodic function can be considered like a periodic function with a limit period. It is followed by f of t is equal to a power t. Here a is equal to 0.5 and so on. Go on verifying this all out because you can verify the particular real time. Okay, and the continuous time signal. So just now we have verified the periodic. Now we are ready to enter the aperiodic signal. Periodic signal, aperiodic signals are required for manipulating the signal. Here, so if substituted a value is a equal to 0.5, so now the aperiodic signal is appeared. The t versus f of t, where f of t is equal to a power, where f of t versus the t, f of t is equal to a power t, where t a is assigned a equal to 0.5. So f of t is calculated measured in graphically and numerically. Okay, so but here the periodic can easily can compare that periodic and a periodic signal. Next, under continuous causal signal or maybe casual signal, these are the signals that are zero for all negative time, or we can consider a signal that does not starts before t equal to 0 is causal signal. It's the important concept there. So we want to manipulate the signal under digital signal processing. Okay, a signal, yeah, a signal that does not starts before t equal to 0 is a causal signal. Okay, so how we are verifying that practically? The here that plus t or minus t or amplitude values also plus or minus a with reference to this causal, maybe anti-causal, non-causal. You can verify in the practically. Here, the signals does not appear, does not start before t equal to 0 is causal signal. Oh, where here? This cases all are 0. Okay, 0. Here 0. Here this side is what do you call the signals are varied. Okay, but here it is there is a distortion here. Noise affected here. Here also noise. Here, somewhat here. Causal signal. The causal is observed like this. Next, anti-causal. Anti-causal is like the reverse of that. Here it is a signal that is 0 for all t greater than or equal to 0 is an anti-causal signal. Here 0, here this case is 0. It's all are 0. Here left side, what you call all are signals are appeared. They are distorted signal. Noise affected signal. Okay, so user can distinguish between the causal and the anti-causal signal. It is a continuous time signal. Okay, non-causal signal, where non-causal is a signal that starts before t equal to 0 is non-causal signal. These are the signal that have non-causal, non-zero values in both positive and negative time. Here both here it is. There are the signals that have non-zero values. Here is a non-zero values, both positive as well as negative. Previously, causal is non-zero values are observed. So non-causal, previous one already we have observed this one. So causal, left side is what you call 0 here, and anti-causal here it is right side is 0 here, and now it is what you call non-causal signal. These signals are these are the signals that have non-zero values in both positive and negative time. Okay, so now under continuous time signal, deterministic signal. A deterministic signal is a signal in which each value of the signal is fixed and can be determined by a mathematical expression in terms of the rule or table, or the future value of the signal can be calculated from past values. Example, any signal which can be precisely defined with a mathematical expression like f of t is equal to the sine of x, is equal to x by mod x. Okay, here also graphically we write to verify the deterministic signal. Of that we'll write to verify non-deterministic signal. Okay, t versus f of t. Here x-axis the t, y-axis f of t. So if it is initially f of t is equal to 0, whatever that go on varying that all f of t equal to either t equal to 0 and so on. Next step. Okay, next t equal to 100, what happens? Then that means f of t equal to 1. Okay, so we have to verify that all deterministic signal. Okay, so the deterministic signal. Next, random signal. Random signal has a lot of uncertainty about its behavior. We are ready to verify that this thing. Okay, the future value of the random signal cannot be accurately periodic or accurately predicted, and can usually only be guessed based on the what you call averages of the sets of signal. Okay, so you have to consider this a simple file, .wav file. Due to this, the signals are varied. Verify that all either is a random signal or not. Okay, so random signal is file is selected. This you can verify this all. Okay, okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.